Display modes, guys. There's 3 types of display modes. Remember, I like to break everything down in the simplest form. 3 types of display modes: A, B, and M modes. Okay. Amplitude, brightness, motion modes. Okay. Use 2 of these. We don't use amplitude anymore. It's obsolete. But you all use brightness mode and you all use M mode. Okay. So we're going to define and discuss the display modes of view and ultrasound. Again, those are amplitude mode, brightness mode, motion mode. Okay. Amplitude mode is the first one. Okay. A mode, displays are created as follows, guys. I tried to, even on the PowerPoint, I tried to make it as simple as I could for you guys to digest it. Okay. Really short chapter. What is it, like 2 pages, 3 pages, something like that? Real short chapter. Okay. Most importantly, I want you to know how the X and Y or Z axis is related to that image. Okay. So, A mode. As a sound pulse is emitted by the transducer, a dot moves at constant speed across the system display. When the reflection returns to the transducer, it is processed and the moving dot is reflected upward on the screen. Like if I had to equate this to something, because we don't use amplitude mode anymore, I couldn't find like an image or a GIF or anything like that to display it. I'd equate it to like EKGs. Y'all ever see how EKGs, you have that one line kind of, you can see it and you know, it's sending a signal. Well, only thing about EKG is getting electrical signals, right? But that dot is constantly moving across, and whenever it gets like a beat or something, it'll actually change, you know, it'll go up or down, right? So that's something I can equate it to, but I didn't want to put that on here because those are electrical signals, not sound signals, okay? But that's what I can, if you need a comparison or something like that, okay? So again, a dot moves across at constant speed, the system display. When the reflection returns to the transducer, the dot is deflected upward on the screen, okay? Amplitude mode. We know amplitude, what amplitude is, right? Okay. It appears as a series of upward spikes, just like this, guys. Looks just like this, like when you're using. Have any of you guys had to do the crash cart yet? Anybody here had to do a crash cart? When they go to the crash cart and have to check it out, make sure it's functioning properly. You get the little strip, and the little strip kind of looks like this. Whenever you're doing somebody, they say, go grab the AED, like in CPR class. You know, it'll be displayed on that little display. Just like this, as a series of upward spikes. Okay, amplitude mode appears as a series of upward spikes. Okay? Kind of reminds us of a big city skyline, right? Kind of looks like that a little bit, a little bit, a little bit. Okay, that's not Houston, by the way. Okay, the height of the upward reflection, of course, represents amplitude. Hence the name amplitude mode. Okay. Strong echoes create tall spikes, whereas weak echoes create short spikes. So this spike right here would be a strong echo right here compared to this spike right here would be considered a weak echo reflection. Okay. The location of the deflection relates to the reflecting structure's depth. Okay. So these structures down here would be deeper. So our x-axis represents depth. These structures along the further part of the x-axis will represent the depth. So these structures will be deeper compared to these structures on this side. Okay. Our y-axis is going to represent our amplitude. Okay. The strength of those signals coming back to the transducer. Okay. We no longer use amplitude mode. Okay, guys. So again, our x-axis represents the reflective depth. X-axis right here, guys, that's our horizontal axis again. Okay, represents the reflective depth. And our that's also derived from the time of flight information. Okay. Of course, our reflective depth is going to be how far something is traveling, right? It's sending the signal out, bouncing off a structure, coming back to the transducer. Okay. Our y-axis is representing the amplitude or the strength of that reflection. Okay. Not a lot to remember on this chapter, guys, except what the definitions are, what the X and Y or Z axis represent, okay, and you know how they appear, and then their appearance. Okay. Question, Mrs. Simmons?
Yes, yes. Derived information from time of a flight.
Mm-hmm.
Who take from whom? which is the first time of a flight, we check it, and we have the information from it, or you mean, I didn't understand this sentence.
The time of flight, meaning the depth of that reflector.
How long
Then
it
we're
takes.
talking about the range equation. That's the time of flight. The
Yeah.
depth of that reflector is going to determine, is going to be determined on the x-axis. So if the reflector structure is really deep, it's going to be represented on along this depth right here. Is a lot deeper than say this depth right here.
We can say here time of a flight.
Time and depth. See, I have it right there.
Yeah, okay.
Yes, ma'am. You sure can. You sure can. Because remember, that's when we're talking about time of flight. We're actually determining how deep a structure is within the body. Okay, so definitely. And remember, we can determine based on our 13 microsecond rule, how far it's traveled and the time it took to travel that distance based on our 13 microsecond rule. Okay, so definitely, we're using both the time and the depth. Okay, A mode is accurate in determining the depth of reflectors, guys. It's accurate determining how deep a reflector is. Okay, this feature is used extensively in ophthalmology. So a lot of times, I don't know, when you guys are at Ben Taub, I know they'll go upstairs and they don't necessarily do an ophthalmologic exam, but they'll do transcranial Dopplers. Okay, again, they use continuous wave transducers. They can use a regular transducer, but you're not going to see anything. But most of the time, when you're doing a transcranial Doppler, they're going to do a continuous wave transducer. So while they're getting the circle of Willis, they'll also get they'll check out the ophthalmic artery in the eye. So they'll put gel on the eye right here, and they'll put a transducer right there and get the velocity or the amplitude of the ophthalmic artery. Okay, you have an image right there, guys. Image 11.3, and that's an actual image of an eyeball. That's an actual image of an eyeball right there. Everybody see that? Okay. So right at the transducer, you see where it's big and black right there. That's going to represent the actual like pupil, or the actual pupil right there, the actual eye. But in different parts of the eye, that's why I just want to say eye, because the eye has an iris and different parts, cones and rods and stuff like cornea, all of that stuff. So you can see on the bottom of that graph, it's representing those echoes are being represented, but you see where it's black right there, where the pupil will be. Nothing is being represented right there, so meaning it's not getting any reflections back, which is why our bar is flat down in that area. We're not getting any amplitudes right there. Okay? But as it travels distally or deeper into the body, you see that it's picking up more and more reflections or echoes. So most important, I want you to know that A mode is associated with ophthalmic ophthalmology. Okay, even though they don't really use that anymore. Questions for A mode, amplitude mode? What's our x-axis, Mr. Seal?
Time or depth.
Time or depth, guys. Time or depth. What's our y-axis? Amplitude, guys. Amplitude. Okay. Brightness mode, guys. Real quick. These are real short. I tried to organize it. Everything looks the same. Okay. B mode or brightness mode displays are created as follows. B mode is the basis of what we do every day. What we do and when we're taking our grayscale imaging, that's also known as B mode or B scan imaging. Okay, works the same way. As a sound pulse is emitted by the transducer, an invisible dot moves at a constant speed across the system display. When a reflection is returned to the transducer, it is processed, and the invisible dot is turned on into a shade of gray, basically. Okay. Appears as a line of dots of varying brightness. Okay, that's how. Know this picture right here, guys. Just know that picture. Appears as a varying. So just like A mode appears as upward spikes, B mode appears as a line of dots of varying brightness. Okay, the varying brightness depends on the strength of the returning echo. All right. Some authors use the term B mode or B scan to describe any form of grayscale imaging. Okay. This is what we do. Our right liver right there. The brightness of the dye indicates the strength of the reflection, hence the term brightness mode. Okay? Strong reflections appear as brighter, whiter dots, whereas weak reflections appear as darker gray dots. Okay? Same thing with what we're doing, right? We have a strong reflection, diaphragm. Isn't it going to be, you can see that whole diaphragm very bright on our image? Okay? A weak reflector, such as fluid, we're not going to get a great reflection from that, right? Because sound is going to be transmitted. Majority of the sound is going to be transmitted through that, right? So it's going to be represented as dark on our image. The same thing with B mode or B scan imaging right here. All right. So here, the x-axis, guys, represents the depth of the reflector. Okay, derived from the time of flight data of a sound pulse. Okay? Depth, time of flight. Okay. The brightness mode actually has a z-axis, which represents the amplitude information when displayed on the oscilloscope. An oscilloscope is like a voltage detector that graphs different voltages. Okay. That's my real quick summary of an oscilloscope. Okay. That's what an oscilloscope looks like right there.
Is this what they use when somebody they want to see if there's a light or then like when this says B right here somebody in the hospital?
And the ICU.
Yes.
Yeah, what is that called? That has a certain term for that. Man, my nursing skills are out of there right now. Any of my people know what that thing is called? The monitor, the heart monitor.
The heart monitor, yeah.
What is that called? Is that most people do this?
I don't know what she was asking.
You know when somebody dies on ER, you know those.
Yeah.
Defibrillation.
That's not an oscilloscope though. That's something
Defibrillation.
else. I forgot what that's called.
Defibrillation. Defibrillation.
Defibrillation? There we go, right there. I trust Dewey. I trust Dewey. Defibrillation device.
Defibrillation device.
I'm on that too. They don't use this kind of technology as far as in healthcare right now. Okay. So again, key thing to remember about B mode, guys, it's the only one that has a z-axis. The z-axis, which represents the amplitude. Okay. So just like amplitude, the y-axis represents amplitude, right?
Mm-hmm.
And the x-axis represents the time of flight or depth. Okay, with B mode, the x-axis represents time of flight or depth. It's the same thing. And the z-axis represents the amplitude.
Not why.
All right. So again, this is my little quick summary of it right here. X-axis, guys, represents the reflector depth. Okay, that's derived from the information from time of flight. Okay? And the z-axis represents reflection amplitude. Okay? Remember, if you ever graph something, the z-axis is basically like diagonal axis, right? So let's see. So a lot of times, I'm just taking this back to
Geometry.
geometry or pre-calculus. When I was in pre-calculus. So this right here, guys, would be our y-axis. This right here would be our x-axis, and our z-axis would be like this. We even use this in CT scans, the z-axis, okay? Which is like our axial plane. Goes in there? Yes. All right. Quick, just in case somebody wants to know what the z-axis is, I just really want you to know that the B mode has the z-axis associated to it, and it represents the amplitude.
Is there only B mode?
Only B mode. It's only B mode. That's the distinction. That's the distinction right there. Appears as a line of dots of varying brightness. There's no y-axis associated with B mode scans. Okay, like I already said, B mode was the first form of grayscale imaging. Okay, it is the basis for all other types of grayscale imaging, including what we use currently as real-time imaging. That's what we use, real-time imaging. That's chapter 13. Okay. B mode, guys. Any questions?
Yeah, what was the x-axis?
The x-axis was the x-axis was the time or depth.
What was the same?
Time or depth. Both of them, A and B mode, the x-axis is the same thing, the time or depth, time of flight or depth. A mode, amplitude mode, the y-axis represents the amplitude. B mode, the z-axis represents the amplitude. Okay. Boom. Motion mode, guys. Right here, motion mode. you guys use this all the time as well. Okay? Whenever you're looking at a fetal heart, or if you haven't used it yet, you will be using it all the time. Okay? In-mode images are created as follows. As the sound is emitted by the transducer, the reflexes move at a constant speed from left to right across the screen. You guys have seen that when they're doing heart rates, right? Everybody's been to MFM at least one time. And y'all see this when they're doing heart rates. Okay. Various squiggly lines represent the changing depth of the reflecting surfaces are produced on the screen. And you see a whole layer of lines. But right where that heart is, you see where it's a little different, right? In mode or motion mode is associated with temporal resolution, right? The resolution that affects the time, okay? Because you want to accurately display the time. Otherwise, we wouldn't get an accurate heart rate or heartbeat if we didn't have great temporal resolution when we're dealing with motion mode, okay, or in mode. Okay? It appears as a group of horizontal wavy lines. So, guys, again, this axis right here is going to represent the depth, because just like you see our sample rate right here, that line right there, that's our sample volume right there. It's sampling this one line, not this whole image. Just this line of information is being represented right here. This same line information is being represented from top to bottom right here, which is why you see the heart right there. This whole line right here, this represents the heart. This whole strip right there. The motion within the heart is being represented by these shifts right here, which is why you see it's almost straight on the top. So that's going to be representing like the skin line right there. As it gets deeper, you have like tissues and fat. You know, as it gets deeper, then when it hits the heart wall, which is right there, you see that line. This line is going to travel through the heart all the way through. All this represents the heart. These represent moving valves within that heart. Okay. And posterior to that, we have just the rest of that sample volume. So this one line is representing just that one slice of anatomy, okay? Not the whole image.
That's mitral valve, right?
Absolutely, that's a mitral valve.
That's wrong. Mitral. The word is wrong.
Yeah, it is.
Spelling.
We're not doing echoes in here. I'll take it off the do. I'll crop that out. Okay. What was your question?
That was mitral heart. That's a baby heart, right?
I think that was just an echocardiogram. I think that was an echocardiogram. That wasn't. I couldn't find a GIF of a live in mode scan. Okay. So in mode is the only display that provides information about a reflector's change in location with respect to time. Okay, which is why our temporal resolution is very important when we're talking about in mode. Okay. Again, this is our sample volume right here, our sample rate right there, representing that one line, you know, or that one slice of anatomy right there. Okay? So when you're measuring, you know, a heart rate, you're gonna go from one beat to the same spot on the next beat, correct? So depending on what you're doing with your machine, because I know sometimes people change their sampling and they'll change the speed. They'll change the speed to very high. And so when you change your speed to high, then you actually have to skip one of these, because it's also getting the heart pump and the release, and it's detecting both of those motions. So you have to skip one and just get the beat. So if I was measuring this, I put my calipers, one right there and one right there. It doesn't matter as long as it's on the same place on the very next beat. Okay. So you just gotta find a place that's similar. A lot of times when we're doing these, they're not that easily detectable, right? You're looking very, very close to see, man, where are these things kind of the same from beat to beat? Because sometimes, especially you're doing a fetus, that fetus is gonna move on you. So it's gonna be really tough to get those. This is an adult person who's not moving, which is why they're getting really consistent beats every time. Okay? So I don't care if you measure it from this point to this point, from this point to this point, or from this point to this point. Okay? As long as you measure it at the same place on the next heartbeat. Right? Okay, so in mode again, it has everything to do with determining the reflector's depth with respect to time. Okay? A line that moves up and down on the display indicates that a reflector is moving further or closer away from the transducer. Of course, if you see that line being represented deeper, right here, being represented deeper, is moving away from the transducer, right? This is our transducer up here. So this line right here is representing deeper. This line right here will be representing closer to the transducer, okay? If that structure is moving. Okay. Hence the name motion mode. Right? A straight horizontal line indicates a stationary reflector, such as like the skin wall, you know, the skin or the fat layer, you know, or the muscle layer. They're not gonna move. When we're talking, we mostly use M mode basically for heart. You know, those are the structures in the body that are moving all the time. All right. The x-axis represents time. You know, all right. X-axis represents time, and on M mode, the y-axis represents the depth of the reflector. Okay? Again, this sample rate is being taken representing superficial to deep. Same thing on here, superficial to deep. Okay, and this is the x-axis representing the time. Okay, all right. Get that? All right. So again, our x-axis represents time. That's why it's constantly moving, because of course time is constantly ticking away, right? So that's why you always see it constantly moving, Okay, that's our horizontal axis. Okay, our y-axis represents the reflected depth, anterior or superficial to deep. Okay, superficial to deep. Okay, and that's derived from our time of flight information. Okay. Since M mode information arises from a single penetration into the body or sampling rate, remember I said that line represents a single sampling rate. Okay, M mode is very high and is equal to the pulse repetition frequency of the system. Of course, right? Because it's representing the entire depth of that image. Right? Remember how we can determine our pulse repetition frequency, 77,000 divided by the depth, right, of our transition, or whatever we're looking at, however much depth we're looking at. Okay. M mode has been primarily used to assess the motion of cardiac walls and structures, and its use is declining. Okay. Okay. This is our quick summary right here, guys. A mode, B mode, M mode. X-axis on A and B representing reflected depth. Okay. On A mode, our y-axis represents amplitude. B mode has no y-axis, so our z-axis represents amplitude in B mode. And our M mode, our x-axis represents the time, it's constantly moving, okay? And our y-axis represents our depth or time of flight. No z-axis on M mode. Okay? Only the z-axis represented on the B mode scan. Okay? I went a little over the guy. We're gonna be a whole review day on Monday. Depending on how quick the review go, you might get out here early. Okay? I have a little quiz for you, of course. It's the day before the test. Have your homework ready on Wednesday, guys. Any questions?
With our work band.
Huh?